Hello everyone, my name is Logan Veronica and we're getting back into our group theory course. Today we're going to be talking about homomorphisms and isomorphisms. Today we are going to cover what a homomorphism is and an example of a homomorphism, as well as isomorphisms. We're going to talk about bijectivity, the definition of an isomorphism, and an example of one as well. Let's take two binary structures, x star and y star. And then let phi be a map from x to y. Phi is said to be a homomorphism if for every x and y in x, phi of x star y in parentheses is equal to phi of x star phi of y. And so a couple of remarks that we need just outright: if E is the identity in x, then phi of E will be the identity in y. You can prove this if you'd like. And for any inverse x prime in x, then phi of x prime will be the inverse to phi of x in y. We're going to start very briefly with an example of a homomorphism. So let's take the integers under plus and 3 times the integer under plus. And so what is 3z? Well, that's just 0, 3, 6, 9, and so on, and also in the negative direction. So then we want to build a map phi from the integers to the partition of the integers 3z. Phi will be a homomorphism, and this is a pretty quick proof. Let a and b and z, let them be integers. Phi of a plus b is going to be 3 times a plus b. But 3 times a plus b is also equal to 3 times a plus 3 times b by our distributive multiplication laws. So phi of a plus b is going to be equal to phi of a plus phi of b, thereby making it a homomorphism. Let's look at a non-example. So let's take the integers under plus and the integers under multiplication, and let's try to build a map. We can't. Phi from z to z, and we will say will not be a homomorphism. Let's take phi of 3 plus 2. Well, that is equal to phi of 5, which equals 5. But that will not be equal to phi of 3 times phi of 2, because 3 times 2 is 6. So the mapping does not correspond to the definition of a homomorphism, therefore it cannot be a homomorphism. Now getting into an isomorphism, we first need to talk about injectivity. Let's first start off by just saying f is a map from x to y. A function f will be 1 to 1. That is also the same as injective, so injectivity is the same as 1 to 1. And that states that if f of x1 is equal to f of x2, then x1 must equal x2 for all x1 and x2 in x. Moving on to surjectivity. Onto, these are the same things. Onto, surjective. Try to memorize those. Being onto is for every y and y, there exists an x and x such that f of x equals y. Basically, every element in y gets mapped to an x. And now we get on to the idea of bijectivity. A function is said to be bijective if it is both 1 to 1 and onto. Also stated both injective and surjective. We say phi from x to y between two binary structures, x star and y star, is an isomorphism if phi is a homomorphism and is bijective, i.e. they are both 1 to 1 and onto. And then we're going to denote this with the same symbol that we use for congruence. X equals squiggly y. That means they are isomorphic. And some structural properties are preserved under isomorphisms. For example, cardinality. X and y will have the same number of elements. And they both will have, x and y, will both have an identity element and inverse elements, which will correspond to one another in the map, as well as if x and y are associative and commutative, then the isomorphism will also preserve that. Now we want to look at an example of an isomorphism and how we might go about proving it. So we're going to take v plus, where v is a vector, a comma b, where a and b are in the real numbers, and our other structural property, or binary structure, the C under addition, so the complex numbers. We want to prove that these two are isomorphic. So first, we have to find a homomorphism between these two. So I'm just going to say that phi of the vector AB should correspond to A plus BI. Well, that would work, and obviously I knew this example, and so then we can then check the homomorphism property. Phi of the vector AB plus the vector CD will be equal to phi of the vector A plus C, comma B plus D, which will be then equal to A plus D, or A plus C plus B plus D times I, which is equal to A plus BI plus C plus DI, which will be equal to phi of the vector AB plus phi of the vector CD. Thus, it is a homomorphism. Now, we need to check injectivity. Well, if we take A plus BI, that equals C plus DI. And that will imply that phi of A, the vector AB, should be equal to the phi of the vector CD. And this means A equals C and B equals D, no matter what. And that is just true. That's our injective map. We know A has to equal C and B has to equal D. So it is injective. Then we want to prove surjectivity. Well, we let A plus BI be in C. Then phi of A comma B, by definition of complex numbers, A and B must be in R. So it is surjective, right? Because the definition of a complex number, take some random A plus BI, A and B come from R. So then phi of that vector AB has to come from R. So it would also be surjective. So we have a homomorphism, injectivity, and surjectivity. Thus, we have an isomorphism. That is all I wanted to cover in today's video. Thank you so much for watching, and have a great day.